All right, welcome back to Nick's Algebraics. So today I'm going to prove that 0.9 repeating equals 1 in 4 levels of difficulty. But before I get started, I want to give a shout out to Egwene Albert is cool 7726 for suggesting this wonderful topic. So thank you very much for that. All right, let's get started. So for the first like basic level of proving this, I'm going to start off by, stating a simple fact people learn like early in school. Like we know that 1/3, that equals 0.3333, you know, 0.3 repeating, like going on a bunch of threes going on forever. So what I can do is I can multiply both sides of this equation by 3. So if I multiply the left side of the equation by 3, here, let me write it out actually. So we have 3 times 1/3 equals 3 times 0.3 repeating. So for 3 times 1/3, that's of course just 1 because the threes will cancel. And 3 times 0.3 repeating, if you multiply each 3 by 3, you're going to get a bunch of nines. And there you go. And you have that 1 equals zero point 0.9 repeating.
I have a question about this.
Yes.
Suppose someone, not me, uh, said, but one equal to that is so unintuitive. Maybe you just proved that three times one third isn't one.
Can you elaborate on that?
Maybe, if he got an unintuitive result, maybe something must have been wrong, like maybe three times one third is not one. What if someone said that to get around the fact that you got this answer?
Well, I mean, let's just break it down. Like 1/3 equals zero point 0.3 repeating. Like that's true. And I can multiply both sides of the equation by 3. That's like a valid step. It's not like I'm dividing by 0 or anything weird. But if you don't believe that, let's say for some reason someone doesn't believe that 3 times 1/3 equals 1, then there's like another way of showing it because you can write 3 times 1/3. That's 3 1/3s. That's 1/3 plus 1/3 plus 1/3. And they all have the same denominator, so you can just add up the numerators and you'd get 3/3. And 3 divided by 3 is 1.
Be that as it may, maybe someone will argue, okay, maybe the first assumption was wrong. Maybe one third isn't equal to 0.3 repeating. But again, not me.
Well, if they don't like 1/3 equals 0.3 repeating, you can always use like 1/9 equals zero point 0.1 repeating, and you can multiply both sides by 9, and you'd get the same thing.
Okay, you're crossing a line now. That's nice. I have a question.
Yes.
What's like, what's the motive here? Why are you trying to prove this? It seems so tedious, in my opinion.
Well, I'm doing this because someone in the comments told me to.
Yeah. Why do anything in life?
That's absolutely right.
uh, it's a toughie. Just kidding.
Okay. Anyway, guys, this is level one. So
Level.
That was more in depth than I thought it would be. Maybe that's my fault.
if you're like like in fourth grade or lower, you should understand this. But
Playing this good to get.
yeah, exactly. But let's I think that's enough for level one. If for some reason the audience is still not convinced, let's move on to level two. So here's my next proof. Let's say that we have a number x. You know you're in level two when you see x. And this number is zero point 0.9 repeating. What I can do is I can multiply this number by 10. Like I know that 10x, like when you multiply a number by 10, you just move the decimal point one to the right. So you're going to get 9.9 repeating. And one thing to notice is that you still have like an infinite number of nines after the decimal point for both cases. So it's not like we're losing a nine because if you have an infinite number of nines and you take one away, like you still have an infinite number of nines. And what I'm going to do is I'm going to subtract these two. So we have 10x minus 1x on the left side. So that's just 9x. And we have 9.9 repeating minus 0.9 repeating. So again, like I said, there's still an infinite number of nines. So basically everything after the decimal point is going to cancel. And you're just going to be left with 9 minus 0, which is 9. And we have 9x equals 9. So if you divide both sides by 9, you're going to get x equals 1. And we said earlier that x equals 0.9 repeating, but it also equals 1. So that means 1 equals 0.9 repeating. So there you go.
You didn't write QED, so I'm not gonna. I'm gonna take this to be false.
QED is how could I? So silly of me. Instead of QED, I'm gonna put a little box because we're modern. QED's for like very old school mathematicians. We're very modern here. But yeah, that's it for level two.
Yeah. Let's see what level three has in store.
All right, cool. It start off the same as level two. So we start off with we have a number x that equals 0.9 repeating. And what I can do is I can write x in a different way. I can write it as 0 0.9 plus 0 0.09 plus 0 0.009 plus 0 0.0009, forever. You can write it like that, right? You can see that when you add these terms up, you'd get this back if you do it like, forever. So this is called a series. This is a special kind of series called a geometric series.
Shout out to the Taylor series video.
Absolutely. This is a geometric series because every single term is a 0.1 times the previous term. So you can see like we're multiplying by 1/10 because the decimal point is just moving to the left one. You can see like this is 0.9, 1/10 of that is 0.09, 1/10 of that is 0.009, and 1/10 of that is 0.0009. So That's called a geometric series. Each term is some number, in this case, 1/10 times the previous term. And now the question is, how do I find the sum of a geometric series? Well, in Algebra 2 or in pre-calculus, we learned that an infinite series where the first term is a1 and the common ratio r is given by this formula, like the sum equals the first term, a1, divided by 1 minus the common ratio. And this is provided that the absolute value of r is less than 1. This only like works when the absolute value of r is less than 1. Absolute value of r less than 1 just means that r is between -1 and +1. And if r is not between -1 and +1, if the absolute value of r is greater than 1, greater than or equal to 1, then this series has no sum. Like it diverges. Like it's just going to go off to like infinity or something like that. But yeah, r is the number, is the common ratio. It's the number we're multiplying each term by. So like I said earlier, we're multiplying each term by 1/10. So r is just 0.1. And a1 is the first term. The first term is just 0.9. So we have a1 is 0.9, we have r is 0.1. So let's plug this into this formula here. So the sum equals a1, which is 0.9, divided by 1 minus 0.1. And 1 minus 0.1 is just 0.9. So you're left with 0.9 divided by 0.9. And a number divided by itself is just 1. So this whole thing adds up to 1. And it also equals 0.9 repeating, like I said at the start. So that means 1 equals 0.9 repeating. And I'll put my little box, which means that the proof is over.
So this assumes that x equals s.
Yes.
And you didn't write that, so your proof is incorrect.
Oh, how silly. Here, let me write here. X. Yeah, this sum is just X.
Well, now you're just defining your answer to be correct.
Oh my God. Guys,
You're caught in a rock in a hard place.
this is why I'll be very clear next time. This is the sum is X.
When you write in your math, whatever, like, I don't know, sine squared of x plus cosine squared of x, do you write that equals 0.9 repeating now?
Absolutely, every single time.
So when was the last time you wrote the number 1? Do you do this every time? If you don't, you should, just to prove a point.
Yeah, I definitely do that every single time. Like when my little sister was born and she was learning 1 plus 1 equals 2, I didn't write 1 plus 1. I wrote 0.9 repeating plus 0.9 repeating equals 2.
Best brother.
I try, you got to get him at an early age, teach him while they're young.
You're corrupting the youth like whichever great philosopher that was that they executed him. Wait, are you gonna get this tattooed along with Euler's identity?
Absolutely. I'll put Euler's identity on my arm and I'll put 0.9 repeating equals 1 on my back.
You're clearly not advocating you get a tattoo necessarily. Nick's just crazy.
Yeah, that's all. But yeah, this is a geometric series. And even though there's infinitely many terms, the series has a finite sum because, like I said, the absolute value of r is less than 1.
You're gonna tell me the sum of the integers is like -1/12 or something.
Oh yeah. Yeah, you can, if this diverges and the common ratio is like greater than 1, you can do like weird stuff and use this formula and like get some nonsensical number. But yeah, the point is that absolute value of R has to be less than 1 for this to be valid. And so you don't like get a sum that goes off to infinity, but you like did some weird math and you made it equal to like some number. But anyway, let's move on to level 4. For this level, I'm going to use something called Maclaurin series.
Ooh, this is reminiscent of something we did recently.
Yes, in my last video, I derived the Maclaurin series for 1 over 1 minus x. So we know that 1 over 1 minus x is just the sum of x to the power of n as n goes from 0 to infinity. So this is kind of similar to last time, the last proof, because it's the same idea with absolute value of x has to be less than 1 for this to be true. So I'm going to pick a number whose absolute value is less than 1. I'm going to choose x to be 0.1. So if I plug in 0.1, I'm going to get 1 over 1 minus 0.1. And this equals the sum as n goes from 0 to infinity of 0.1 to the power of n. All right, so I can just clean this up a little bit. So we have 1 minus 0.1 is just 0.9. And again, that equals this sum. Just to make this look a little prettier, I'm going to multiply this by 10 over 10. Just so I don't have like a decimal in the denominator. So I just have a better looking fraction. So 1 times 10 is 10, and 10 times 0.9, like again, you just move the decimal point 1 to the right, and you're going to get 9. So this whole fraction becomes 10 over 9. And let me just expand this sum here, because when n equals 0, you're going to get 0.1 to the power of 0, which is 1. And then when n equals 1, you're going to get 0.1 to the power of 1, which is 0.1. When n is 2, you're going to get 0.1 squared, which is 0.01. And then you're going to get 0.1 cubed when n equals 3, so 0.001, and so on. So now what I'm going to do is I'm going to multiply both sides of this equation by 9. So 10 equals, and I'm going to distribute the 9 to these terms. I'm going to get 9 plus 0.9 plus 0.09 plus 0.009. We saw this earlier, 0.9 plus 0.09 plus 0.009. That's the same thing as this right here. That's the same thing as just 0.9 repeating. So this is just 9.9 repeating. And if I subtract 9 from both sides, you're going to end up with 1 equals 0.9 repeating.
You said if you subtract.
Yes, because like 10 minus 9 is 1. No, you can do that with anything. Like you don't have to have a variable. You can have like 3 plus 5 equals like that's 8. That equals like 4 plus 4. And I can subtract 1 from both sides, and I can say like 3 plus 4 equals 4 plus 3. I just like took away the 1. And you get something. You can subtract or add, anything to both sides of any equation.
But your answer here is wrong because you plagiarized the previous level. So this is incorrect. This is proof by plagiarism.
Oh my God. How dare I?
Let me think, Mr. Algebraics, does this mean that 0.0 repeating 1 is 0?
That's a very good question. If you have 0.0 bunch of zeros repeating, and then a one. The thing about that is when you have an infinite number of zeros, you will never put down that one after the zero. So you basically just have an infinite like string of zeros. So yeah, this pretty much equals zero.
Mm, my intuition.
Yeah, exactly. There you go.
I'm very angry right now. I don't know why.
Yeah, likewise.
Can you go back to level 1?
Sure.
Sorry, level 0.9 repeating.
Of course.
That's it. Just wanted to make that joke. Can't it be? You should have proved this as 0.9 repeating over 3 is equal to 0.3 repeating. And you have, 0.9 repeating over 3 plus 0.9 repeating over 3 plus 0.9 repeating over 3.
I like that.
In fact, your 1/9 is equal to 0.9 repeating, 0.9 repeating, 0.9 repeating, 0.9 repeating.
That's
You
perfect.
should just abandon the digit 1.
Absolutely. The one is just very unnecessary. All ones should just be written as 0.9 repeating. And you know what? Even though in all these four levels I've been showing different ways that 1 equals 0.9 repeating, you can take this one step further and say like 2 equals 1.9 repeating. And you can even say like 1.5 equals 1.49 repeating. I'll use the bar this time. Yeah, you can say like 3.63 equals 3.62 with a bunch of nines after. So you can do this with a lot of number, with any number pretty much.
I think all your roots.
No, my subscribers would never. My subscribers, you know, my weakest subscriber bench is like 250. So they know. They're tough.
Being 249. It looks correct, but we reject it nonetheless.
All right,
Yeah,
that's
I mean, not even because of the math. Just because, like,
Just because it's you.
yeah,
yeah.
exactly.
Yeah, I feel that. That's pretty typical of people that I like show this proof to. Anyway, don't forget to like, subscribe, and comment, guys. I'll see you guys in the next video.
Bye.
Peace.